save it. So 1.4. So we're still talking about functions and their graphs. Functions. Determine whether a relationship is a function, find domains of function, find models, real life, evaluate. So many everyday phenomena involve two quantities that are related by some rule, kind of a function. Yep. In mathematics, equations formulas often represent relations. For instance, simple interest earned on $1,000 for 1 year is related to the amount of interest rate R by the formula this year. So the amount of interest you gain is compared to the amount of time that's progressed. We have this 1-to-1. Now the formula this year says it's called a function. A function f from a set A to set B is a relation that assigns to each element x in set A exactly one element y in set B. The set A is called the domain, and the set of inputs of the function f, and the set B contains the range. So our x values are mapped to y. So 1 is mapped to 2. So if you plug 1 into the function, you get 2 out. That's all it's saying. It's a more mathematical way that we talk about it, because we wouldn't bring this up in Algebra 2 or Algebra 1 because it's a little bit more complex definition of it. But this is the same definition. It's pretty much the domain is mapped to the range. So the domain to the range. The function takes us from our x value to the y value. And that's it. That'll help. So they gave us this below. So time of day, 1 p.m. It's apparently 9 degrees Celsius. At 2 p.m. it's 13. At 4 p.m. it's 15. At 3 p.m. it's 15. At 5 it's 12. At 6 it's 10. This is a function. 1x, or each x is mapped to at least one y. It could have 2. That's fine. But we can't have 1x going to 2 y's. It can't have the same value and still be a function. So each element of A must be matched with an element in B. Some elements in B may be matched with any element of A. 2 or more elements of A may be matched with the same element in B. An element in A is the domain and cannot be matched with 2 elements in B. Okay? Because that's when we fails the vertical line test. If we draw a straight line up and down and it crosses more than once, it is not a function. Okay, 4 ways to represent a function: verbally, kind of writing it out in words; numerically, listed tables or ordered pairs; graphically, by a graph; and algebraically with an equation. Determine whether the relationship y is as a function of x. The input value of x is a number representatives from a state, and the output y is the number of senators. So can we say this is a function? So the number of representatives from a state going to the number of senators. Oh yeah, it's down here. The variable description does describe y as a function of x. Regardless of the value of x, the value of y is always 2. Such states as a constant. Determine whether this is a function. So 2 to 11, 2 to 10, 3 to 8, 4 to 5, 5 to 1. What do we say? This does not describe y as a function of x because the input value of 2 is matched with 2 different y values. This right here. This right here makes it not a function. As if we looked at this at a graph, does not pass the vertical line test. Determine whether the relationship here represents y as a function of x. Is this a function? So do we have any 2 points? No. So, yes, it is a function. It passes the vertical line test. If we would draw a straight line and see and carry it across that entire graph, would it cross twice? No. So we're good. This is a function. Each input value is matched with exactly one output. Because if we had another point put here, then it wouldn't. I would have 2 at 1. So it wouldn't work. Representing the function by sets of ordered pairs is common in discrete math. In algebra, however, it is more common to represent functions by equations or formulas involving two variables. For instance, this one here, y equals x squared. Y is a function of x. It's a quadratic, or U-shaped graph. Because as long as we can write y by itself, we're good, and it's going to be the set of all values in the domain. For example, we know that this is true. Suppose, for instance, this function, that is a function. Okay, let me back. So when using equations to represent a function, for example, you know that the equation y is equal to 1 minus x squared is a function. It is a function. Describes y as a function of x. Suppose, given this function the name f, then you can use the following function notation. X is the input. It's the values we plug into the function. Yes? Nothing too new there? F of x is the output. We normally call it y in most cases. We write it as y or f of x. And f of x is equal to 1 minus x squared is the equation, the actual equation of what we would graph. Okay? Now the symbol f, this here is read as the value of f at x, or simply f of x. So this here is f of x. The symbol f of x corresponds to the y value for a given x. So we can write y is equal to f of x. Or really, it's saying we can switch f of x and y. They're the same thing. Keep in mind that if f is the name of the function, whereas f of x is the value of the function at x, keep that in mind. Those are different. F of x is the value, f is the name. Tori is a name, Tori Daughtery, that is you, yes? Because there's more than one Tori, but not more than one of you. Kind of see the difference? So this function here, that's really the only difference between the two. Now, we can plug in values into this. So f of negative 1, f of 0, f of 2, and get a value out of it. That's where we get this here. Is if I plug in negative 1 into this here, so we plug it in wherever x is. Y'all remember doing this in algebra 2? And then we simplify and get 5. Or we could plug in f of 0. Or we could plug in f of 2. And when we plug it in, we would get a value out. That's about it. Convenience, for instance, so we can have independent values. You can use other letters instead of x, so we can use f of x, f of t, g of s. It's the same thing when we plug in values. Consequently, the function could be described as this here. I can just put a box. It's the same thing. It doesn't really change anything. Now, the next thing we're going to talk about is a piecewise defined function. A piecewise defined function has more than one function attached to it. Yep, it would do that. Like this here. This is a piecewise function. Now, depending on the value of x is going to depend on which one we use. So if we said f of negative 1 is what we're going to do first. Is negative 1 less than 0 or greater than or equal to 0? Less than 0. So this statement right here is true, yes? So with a piecewise function, we're going to use the equation that's attached to it. So any value less than 0 is going to use this function here. Any value of 0 or greater will use this one. So f of negative 1. So what am I going to do? I'm going to plug negative 1 in for x squared. So I have negative 1 squared plus 1. What is negative 1 squared? Plus 1 is? Let's try 0 next. F of 0. Which one would we use? X minus 1. So we would have what? 0 minus? And how about f of 1? So we use the same one again, yes? The x minus 1? So what is 1? Is it greater than 0? Yep. So 1 minus 1 would give us, so whatever the value of x that we're trying to evaluate for these here is going to depend on which one we use. It'll tell us which one we use. Questions on this here? Not too bad. So for negative 1, we use this one here, so we get 2. And the last one we got 0. Any questions on anything we've done so far? We might come back to something like that, a step function. I don't, if it doesn't show up. Now the domain of a function can be described explicitly, or it can be implied by the expression to use to define the function. The implied domain is a set of all real numbers for which the expression is defined. What values we can plug into the function. What values of x we can use. Because up till now, most quadratic, absolute value, constant functions, cubic functions, any functions we have used, except for rational functions, have had all real numbers as the domain. We can plug in any value of x. Here, there's two cases that don't work. And one of them is if the denominator is 0. I'm just going to put an asterisk up top. The denominator is 0. It doesn't matter what's on top, but if the bottom becomes 0, it doesn't work. So any value that would make the denominator 0 is not going to be part of the domain. Now we also talk about radicals, our square roots, mostly even roots. Even roots. The number inside here cannot be what? Negative. Because if we have a negative number inside an even root, that's why I put 2 in. Because no matter what n is, it's always going to be even. Any even root, any positive even root, we cannot have a negative inside because we get an imaginary number. Yes? Because the square root of negative 1 is I. We can't have a negative inside of an even root. So if either one of these cases pop up, we will have restrictions on what can be the domain. Okay? So on some of these, like this one here, we might have restrictions on the domain. The domain excludes x values that result in division by 0. This here has an implied domain consisting of all real numbers other than x is equal to plus or minus 2. So I see both of y'all do have your graphing calculator. Let's graph this and let's see how this looks. So in there you can hit y equals, or you can turn it on and then hit y equals. So alpha, y equals enter will give you a fraction. And then we do 1 over our x, squared minus 1, or 4, minus 4. You see how there's two distinct cutoffs? Going straight up and down, it came up on 2 parts, and in the middle, it had a different part. Those 2 lines where that meets is our plus or minus 2. Because we can't have a value of 2. It just won't work because the denominator would be 0. And that's what it looks like. Is we have those spots where the denominator cannot be 0. We cannot plug 2 into it. It just doesn't work. Does that make sense? Now, looking at that there, the graph went straight up, yes? It went straight down. Pretty much everything on the y-axis is covered. So the y value for this here, or the range, would be all real numbers. It works for any, we can get any number out, but we can't plug any number in for this one. Another common type of domain that is used to avoid are even roots of negative numbers. For example, this here, as we just said a minute ago. The domain excludes x values that result in even roots of negative numbers. So anything that would be negative in here. Well, that's anything less than 0. So it's defined to be x is greater than 0, so the implied domain is on the interval of 0 to infinity. In general, it's whatever would make whatever's inside there negative. It's not that we can't plug in negative numbers, it's just what would make it negative. And to kind of answer your question, Tori, would be something like, if it had plus 3, because negative 3 plus 3 is 0, yes? So it would change it from, instead of being the smallest number 0, it's now negative 3. Does that make sense? We could also have the case that instead of this, the square root of negative x. That's going to change this to this here. Because now, because it's a square root of negative x, I can only plug in negative numbers so that I don't get a negative out. So some of this stuff you can graph. Like if you graph the square root of x, okay, I see that it's only here. So the graph will show us some of this. Any questions on this here? Find the domain of each function. So looking at this here, what is the domain? Well, it's just points, isn't it? It would just be those x values, because since it's just points, it's just going to be the x points. Now, it doesn't ask for the range, but if it was going to ask for the range, what would it be? The y. So we would have, I think, negative 1 is the smallest, 0, 4. Now, even though 2 shows up twice, we only have to put it once. I'm going to only list it once, because I've listed all the range values. But it's not connecting those two. We have 2 twice, but I'm only going to put it once. How about this one here? Well, it's a function, yes? Is there anything that would make that denominator 0? Negative 5, yes? But would any other number work? But yeah, because negative 5 is the only thing that will make that 0. So we have all real numbers except negative 5. And this is a way to write that. So you could say all real numbers except negative 5. You can actually write that out. This is actually what it says. All real numbers except negative 5. That's a shorthand way to write it. Questions on this here? So the volume of the sphere is given by this equation here. Is there any way that we can make r cubed be divided by 0? No, there's no radicals. Is there any way that we can get an undefined term? So what's the domain here? All real numbers. And it works out the range for this here is all real numbers. I would have to graph that one to kind of see what the range is. But that's an easy way to get the range, just graphing it. Last but not least, this one here. Can we have some undefined terms here? If this thing equaled, well, negatives, yes? And where does it change from positive to negative? At 0, yes? So what I'm going to do to find that is I'm going to just set this thing equal to 0. What would make this thing 0? So the first thing we can do is, okay, let me change one thing. I'm going to back up a second. What did we say about 0? This has to be greater than 0, yes? Now, the reason I backed up was because in the back of my head, I was shouting at myself. How do we know which direction to go? Because we have to say that it's either bigger or less than, like we saw earlier with the square root of x. Well, that's greater than 0. Well, if it's negative square root of x, it's less than 0. How can we tell? So we'll add this. This will tell us. And really, we can say it has to be greater than or equal to 0, because 0 still works. And we can do it this way. This will tell us. All right? So we'd still subtract 4. That doesn't change. And that gives us negative 3x is greater than or equal to negative 4. Now what? Yes. And anytime you multiply or divide by a negative, and this would be, so the domain would be what? X is less than or equal to 4/3. Now there's going to be some restrictions on the range will not be every value because most square roots, more like a curve, starts here, curves. It doesn't cover all the range, but it would cover some of it. And the easiest way to find that is just graphing it. It'll show you kind of what they are. Questions on this here? Not too bad. So the domain of the first one is that, excluding x values for the second one, the denominator, the domain of G is all real numbers except for negative 5. Got that one. Because of the function represents the volume of the sphere, the values of r for the radius must be positive. Okay. Slipped my mind. We can't have negative radius. Makes sense. And the last one. So we solved that. Got our answer. Note that the domain of the function may, for this equation, you would have no reason to restrict r to be positive. Let's see here, for the instance, the equation, you would have no reason to restrict the values to be positive, but because the physical context implies that the sphere cannot have a negative or 0 radius, we have to do it. So if we're talking just, this is an equation, hey, it could be all real numbers. But physics kind of restricts us. Says you can't have a negative volume. But that's it. Questions on this here? Okay. Not going to look too much at that. But I want to look at a step function. I'm trying to remember the symbols. I think it's that. It's our step function. And what the step function is it rounds down. No matter what it is, it rounds down. Okay, actually, I'm going to take that back. Okay, we're good. I'm not going to talk about those yet. Those aren't for another 2 days. And really, getting into this here is it's actually, yep, I'm going to do the correct bars that I just saw a minute ago. It looks something like this here with 2 sets of bars. And so it's steps. So a basic one from 0 to 1 is right here. And then as soon as it hit 1, so from here to here, it's at 0. As soon as we hit 1, it jumps up to here. Make sure I got this right. Yep, okay. Have that wrong. Okay, as soon as we hit 1, it jumps up to 1. And all the way until we hit 2, it is at 1. So 1.99999 is still 1 in the step function. But as soon as we hit 2 on the x, it is now at, so no matter what number we get, so in here if we have 2.76492, it's still 2. It's still 2. It pretty much, you drop that decimal. Does that make sense? And we'll cover those later, but that is coming up eventually. Don't worry about the can or volume. Difference quotient. Okay, this is something we will look at. This is calculus based. The difference quotient, one of the basic calculus employed is this ratio here. It's called the difference quotient, as illustrated in example 11. Now, what we do to find the difference quotient or evaluate it is we're plugging it in here. I'm going to draw a big old line. Now, to find it, so this is f of x plus h. So all of these spots here, we're going to plug in f plus h. So here we're going to have f plus h minus 4 times f plus h plus 7. Because we just did that part there. And not f. If I can read correctly, 8x plus h. And then here we just have our normal equation because we're plugging in f of x. And it's all over h. We're good? And from here we would simplify. Now we still have h on bottom. This here simplified out is going to be x squared plus 2xh plus h squared. You remember doing distributive? So it's a distributive property. I'm going to write this on the board. It's pretty much saying we have x plus h times x plus h. X times x is x squared plus xh plus xh plus is how we got it. I just skipped that step, multiplying it out. Minus, we would distribute, so we have 4x minus 4h plus 7 minus combine like terms. What is x squared minus x squared? Negative 4x minus negative 4x. 0. Well, negative, I'll write that one out. Because here we'll have negative 4x. Well, this negative and that negative make a. So you have those two and they cancel. So you have 2xh. I don't have an h squared over there. We already dealt with that. Minus 4h. 7 and 7 cancel out. All over h. So this here, so we don't get confused, is gone. That's unfortunate. So we got this here. What do you notice is common in all these here? H. I'm going to factor it out. So h out of h squared is just h plus 2x minus 4 all over but there's a difference quotient for this equation. Where h is not 0. Because we have 0 in the bottom of the fraction, so it can't be 0. That's it. So this is 1, 4. So 5 and 7. So this is the homework for 1, 4.